Okay, this is lesson 1-4, piecewise functions. We've talked about it before. We're going to do it again because it's very important that you know. Piecewise functions are functions defined by different formulas for different intervals of the independent variable. Okay, so basically usually that's your x. So basically they have like subdomains. So like you're going to use formula 1 if they give you a certain domain here. This next one, if they give you a different domain, formula 3 for a different one, you can see any number of ones there. Now, here's some examples of piecewise functions. First of all, we have the absolute value function. You may not realize the absolute value function is a piecewise function, but it is because we know the absolute value of x is x if x is greater than or equal to 0, or it's the opposite of x if x is negative, if it's less than 0. Because remember, absolute value is always positive. So if we wanted to like graph this, and we pick some things, let's see, -2 to 2. Well, if this is the absolute value of it, then this would be 2, 1, 0, 1, 2, right? So this is a piecewise function. So if we plot these points, let's look and see what it looks like. Notice it's a V shape. It goes on forever and ever this direction and this direction. So that is an absolute value function. Is it continuous? Yes, because you can, put your pencil down and draw it without picking up your pencil. As far as the domain, there is no definite left or right. So for the domain, I know it's from -infinity to +infinity. It's all real numbers. The range, however, notice that there is a bottom y. There's a bottom y. So the bottom y is 0. So the range is going from 0, or the y's are going from 0 up to infinity. Where is the function increasing or decreasing? Well, remember when you're dealing with this, you're always looking at left to right. That messes people up a lot for some reason. But from left to right, it's decreasing from -infinity to x is 0. And then it's increasing from 0 to infinity. So notice on the intervals of increasing, decreasing, constant, you're never going to use brackets. Things are changing at that point, okay? So never use brackets for that. The brackets are only needed for domain and range. Okay, so these next two, the ceiling function and floor function, that's like the greatest integer function. It's step functions. The ceiling function is defined as the function where that little symbol with the x with the little top part is the least integer that is greater than or equal to x. So if we're going to graph this, okay, we're going to figure out what this means. Let's start with 3, and let's do like, say, 2.5 or 2.5, and 2, and 1.5, and 1, and 0.5, and 0, and it goes on, but we'll get the gist of it here. So if I want the smallest integer that's greater than that one or equal to it, so if it's equal to it, then I know all these integer ones are the same thing, right? But let's look at the ones in the middle here. 2.5, if it's 2.5, I need an integer, a whole number, that's greater than that one. So that's still going to be 3. Because I can't go to 2, 2 is less than it, but it's the smallest one, or so basically the first one I'm coming to that's bigger than it. So this would be 2, and this would be 1. So let's see how that goes when I graph it. I know I've got 0, 0, 1, 1, 2, 2, and 3, 3, but I also have 2.5 and 3, so that's still like right here on this line. So it turns out you have a little line, and then you're going to have an open circle at the end of that little line for each one of these. So this is a solid. It's going to be a little line, open circle. Solid, a little line, open circle. And it repeats for as long as our domain says we need it. Let's see, we're going from -3 to 3. So we can kind of continue this pattern and see where it's going to go. But notice the solid dots are at the points, the 1, 1, 2, 2, 3, 3, like that. Then the floor function is very similar, except, you see how it's got the little signs on the bottom here? It is the greatest integer less than or equal to x. So again, if we make our little chart here, we're going to start at the bottom this time because, see, I'm starting where they have the solid bracket. So -3, -2.5, -2, -1.5, -1, -0.5, 0. I'm running out of room. Let's see if I can move it up a little bit. There we go. All right, so if it's the greatest integer less than or equal to that one, so the ones that are equal, I know I can just go ahead and put those numbers there like that. But on these ones that has halfway in between, well, let me plot these first. Maybe this will help me figure it out. So -3, -3, -2, -2. Okay, so I know I'm going up to at least 2, 2, right? Because it doesn't include 3. All right, so if I go to -2.5, I need the greatest integer. So a number, the first one I come to that is less than or equal to this one. So less than this one would be -3. Less than 1.5 would be -2. Less than -1/2 would be -1. So notice this part is going to go this direction. Open circle is going to be on this side. So you see how I still have the dots circled in on the points that we have, but now it's kind of going the other direction with the open circle. So there you have it. So those are a little bit complicated to figure out, but if you really think about it, it's not that bad. Okay, so when we evaluate piecewise functions, then you have to pay attention to the domain here on all three of these, okay? Because we have to look at the x value they give us and determine which formula or which function piece that I'm going to use based on where the x value falls in the domain, the subdomains here. So notice on this first one, if f of 12, well, 12 is bigger than 3, so that means I got to use this last one here. So this gives me 5 minus 1/2 times 12, which is 5 minus 6, which is -1. So you're just using your order of operations once you plug that in. If f was 2, that means x is 2. I'm going to use that middle one there. So that's just 2. There's really not anything to plug in, so that's just 2. That one's nice. Okay, so if I have f of -5, -5 is less than 1, so I'm using this top one here. So this would be -2 times the absolute value of -5 plus 1, which is -2 times the absolute value of 4, which is -2 times 4, which will be -8. Not so bad. And then the last one, f of 0 here, 0, oh, that's still in the same one, right? Sure is, it's in the same one. So -2 times the absolute value of 0 plus 1, which is -2 times the absolute value of 1, which is just -2 times 1, which is -2. Okay, so example 3. Here we have one where x is greater than 2 or x is less than or equal to 2. So these are our restrictions. So we got to figure out where they fall in this category. So f of 6, that would be greater than 2. So this would be 3 times 6 minus 7. 18 minus 7, that's 11. On the next one, -3, that's less than 2. So that would be -3 squared minus 1, which is 9 minus 1, which is 8. So be careful when you plug in a negative that you use the parentheses and the exponent goes on the outside, because if you forget that, then you got a problem. All right, so name the graph. I find students kind of struggle with this part, but you need to be able to do this. First thing we're going to do is look at the areas of the x's. So notice we've got one piece that goes from x of, what is that, 2 on forever, right? So that means this would be if x is less than 2. That would be that yellow piece right there. And then, let's see, this piece right here in the middle, that's going at x of 2 to an x of 5. So, and notice how the 2 would have an or equal to because it's a solid circle. So that's what that piece is. And then this last piece right here, 4 to infinity, goes on forever, not 4, 5, x of 5. So we're going to say x is greater than or equal to 5. Okay. So those are our pieces. So to find out what the equations are, sometimes that's a little trickier. I'm noticing that this middle one, that's just the equation, it's zero slope. That's just y equal to 3. So I'm just going to go ahead and put that one. Obviously, that's what it is. Let's see, the top one there in the yellow, the y-intercept is 5 because it crosses right here. But I need to find the slope. So I'm going to pick any 2 points on the line, and notice my slope is down 1, right 2. So it's a negative 1/2 x plus 5, because 5 is my y-intercept. And then, let's see, the next one down here, the slope on this one, I can pick any 2 points on the line. Oh, the slope here is negative 1, so negative x. But I need the y-intercept. I can either solve for that, or I can kind of like back it up. Oh yeah, that's going to be 7, so plus 7. So you can either, write your equation for it and figure it out, or just kind of back it up like you see right there. So that's that one. Now this next one on part B, notice that looks a little bit more complicated. You might want to pause it and try it on your own. See if you can do that. But this piece right here, let's see, that one would be, yeah, if you want to pause it and try it on your own and then come back, see if you got it right, that would be a great idea. This one would be x is less than or equal to 2, because notice it's a solid circle at 2, and it goes on forever. It's got an arrow on the end. That middle chunk between 2 and 5, so 2 to 5, notice neither one has or equal to by it because they're both open circles. And then this last one is 5 or greater, so x is greater than or equal to 5. So those are our 3 pieces of the domain. Now writing the equation on this one. We've been writing this equation for a while. We've kind of had some practice now, but y is equal to a times x minus h squared plus k. Okay, so this is my vertex point, which is the point 0, negative 3. So this is my h, and this is my k. Sometimes you have to solve for the a. This one you don't really have to, but I want to show you how anyway. A happens to be 1, but I'm going to show you how you would do that. This point right here is the point 2, 1. So that's going to be my x comma y. So basically, let's see if I can write it. Will it show up down here? Yeah, it will. Okay, great. So I'm going to have 1 equal to a times 2 minus 0 squared minus 3. So notice I filled in what I knew. And now I'm going to solve this. I'm going to add the 3 over here. 2 squared is 4. So I get a equal to 4 equal to 4a. And so that means a is 1. And of course it should be positive because it's opening up, but a is 1. So the equation of this line would be y equal to 1 times x minus 0 squared minus 3, which if we clean that up would give us x squared minus 3. So we'll put that in the first spot up there. All right, so this middle line here, that one's an easier one. That's just y equal negative 2. So So I'm just going to put -2 there because it's a 0 slope. And then the other one is going up. So the slope would be, what is that, up 1, right 1 on each of these. So slope is 1, so it's 1x. What would the y-intercept be on this one? Let's see if I kept it going. Oh, y-intercept would be the same thing here, so that's -3. Awesome. Okay, so when you go to graph a piecewise function, you need to again pay attention to the domain restrictions here, and we're going to use that, and we're going to make tables. And if you make a table, I find it helps out tremendously on trying to graph something. So let's see if I can kind of squeeze this in here. This is for the first one. X is less than or equal to -1. So I'm going to go -1, -2, -3, that kind of thing. And the thing is, you want to, sometimes just a couple points will be fine. Other times you need more than just a couple points. It depends on what shape the graph is to how many points you're going to need to see what it is. So for instance, I know this one has squared, okay? So this is quadratic. So I need to see that U shape, okay? So I'm going to plug in -1 up there, and that should give me -1.5. If I plug in -2, I get 1. If I plug in -3, that gives me 2.5. If I plug in -4, I get 3. -5, 2.5. And if I keep going, go one more, this is 1 again. Okay, so -1, -1.5. So that's down here. It's a solid circle because it's or equal to. And then -2, 1. And 4, -3. Oh, I'm sorry, 4, +3. -3, 2.5. And notice it's coming back down on this side, so it's going to look like this. So you got to make sure you can see the shape, okay? And we do know it goes on forever. There's no ending on that side. All right, so let's look at the middle piece here. All right, -1 to 4. So -1, not -2. Got to go the other direction because we want to go to 4. So 0, 1, 2, 3, 4. It'd be nice if we had a little bit more room on this one. Okay, if we plug that into that second equation there, second formula, we get 5, 2, this one's -4. I'm skipping some. So that means, let me do this in a different color just for fun. I don't feel like doing all of these. There's just too many. Okay, so as long as I can see the shape, we're in good shape. So -1, 5. So this is an open circle because it doesn't have or equal to by it. 0, 2. That's here. 2, -4. That's here. 6. No, I didn't do 6. 6 is too far. I'm going to 4. 4, 2. Oh, open circle there too. All right, so that means it goes like this. And it's absolute value, and it should be a V shape. If it's not, I got a problem. Okay, so I could have done the points in the middle. I just was trying to go a little bit faster. And then this last one. This is a cubic one, right? So cubic, but we got to start at 4. So I'm going to do 4, 5, 6 and see what happens. Okay, so 4 would be -6. 5 would be 1. 6 would be 2. 7, 3. 8, 10. That's probably too far off my graph. Okay, so 4, -6. Close circle. 5 is 1. 6 is 2. 7 is 3. Now, notice how it looks like a line right there. So if you didn't know what that graph was going to look like, that's going to cause you some trouble. But I know that it's like half a parabola up and half a parabola down. So you need to know what it's supposed to look like in the shapes of these functions to be able to graph it properly. Okay, so the next one is a word problem, applications from your life. If you ever, well, you probably heard your parents talking about paying taxes, but if your taxable income is at least $0, but not more than $30,000, then the tax rate for you would be 15% of any amount over a certain amount. If you have $30,000, but not more than 65, then you're paying $4,500 plus 20% of the amount over $30,000, and so forth. Okay, so let's write this down. Write a piecewise function, giving the tax owed by a person whose taxable income is X. All right, so the first one is just 15%. So remember, you got to change it to a decimal. So that one's not bad. That's for any X, well, basically X is between 0, I should say, even though we know that's true, and 30,000. Okay. The next one would be, well, we've got 4,500 plus 20% of X, but it's not all of it. It's only on the amount over 30,000. So I have to say X minus 30,000 right here. So this is for X between 30,000 and, oops, I can't have an or equal to, because I already have one up on the top one, right? It can only be in one of those places. It can't be in both. All right, so 65,000. All right, and then the last one would be 11,500 plus 24% of the number that's above 65,000. And we could clean this up a little bit and combine our like terms and not have this parentheses and distributed property going on, but, oh wait, I need to put the 65 on the other side. So this would be between 65,000 and less than or equal to 125,000. Okay, so normally when you see piecewise function, you know, you'll have several pieces. The domain restriction is going to be there and let you know what you need to worry about. I wonder why it's not erasing that, because I did it too long ago. It just wasn't too pretty, so I was trying to fix it. Okay, there, a little bit better. Okay, so anyway, it has this different pieces, and you see the big bracket in the front, and it's named whatever. I did T of X right here. All right, so part B. Evaluate the function to find the tax owed by a single person whose taxable income is $68,750. All right, so that means, if I want to find the tax for $68,750, then that is in this last one, right? So it would be 11,500 plus 24% of the part that is less than, greater than 65,000. It's got to be what's over that. So 11,500 plus 0.24 times 3750, which ends up being, what's that, 900? So that gives us $12,400 in taxes. Okay, so last example, example 7. In August, Orlando Utilities Commission supplied electricity to residents for a monthly customer charge of $8 plus a little over 10 cents per kilowatt hour for the first 1,000 kilowatt hours used in the month, and a little over 12 cents per kilowatt hour for all electricity over the $1,000 in the month. So what's the charge for using 920? All right, so let's look at our key information here. Well, we know we got this $8 monthly charge. Let me do that in a different color, because when I do it in that color, it looks like I'm scratching it out. Okay, so $8 plus this much for the first 1,000. So that means for 920, this is going to be $8 plus, oh, it's in cents, so I better change that, right? 0.10143 times 920. And if you put that in your calculator, I think you get 101.32. Okay, so but if it was $1,500, then that one's a little bit more complicated to figure out, because remember, you get two different charges for over 1,000 and under 1,000. So you're going to have $8 for the monthly charge plus 10143. I don't know why that money looks so terrible there. And that's for the first 1,000, right? Plus you're going to have the increased rate, which is 12143 times the difference there. Okay, so if you got 1,500, the first 1,000 is at a lower rate, but the extra above that is at the higher rate. So that gives us let's see, 170.15. There you go. All right, so when you have actual numbers, it's really not that bad trying to figure it out. But here they're asking us to actually write the function, okay? We want to write the piecewise defined function. So that's what makes it hard. Because like initially, you know, if x is less than or equal to 1,000, it's pretty straightforward. It's just $8 plus the 0.10143 times x, you know. But it's when it goes over that 1,000 that it becomes a problem. So let's look at how we fix that. So if x is greater than 1,000, then I'm still going to pay this $8 fee. I'm still going to have the initial charge for the first 1,000, but now for the ones that's after that, I'm having to pay more, that increased cost for x minus 1,000. So basically, we just kind of need to clean that up to be able to write our updated, our piecewise function. So if I clean this one up, that would give me 8 plus 101.43 plus, let's see, that's distributive property, so 0.12143x minus 121.43. So that gives us, if we add all the like terms together, 0.12143x minus 12. So our function here would be 8 plus 0.10143x, and that's where x is, well, let's say it's between 0 and 1,000. And then if it's greater than 1,000, you got 0.12143x minus 12 if x is greater than 1,000. All right, so that's what it looks like. So you just have to be careful with that part and be able to clean it up. All right, so the rest is for you to work. So I'll post those answers and you can check it and before you send it to Shobi, and let me know if you've got questions.